This is Bukya Krishna, rule number 20951A2130, branch aeronautical engineering. So today I want to discuss about mechanics of solids. As a topic, I selected shear force and bending moment of a cantilever beam subjected to UDL, means uniformly distributed load. So first we want to discuss about moment and bending moment. What is the difference between moment and bending moment? Moment, it is a product of force and perpendicular distance between line of action of the force and the point about which moment is required to be calculated. And the next is bending moment. Bending moment, the moment which causes the bending effect of the beam is called bending moment. It is generally denoted by M or Bm. And shear force at a section, the algebraic sum of the vertical forces acting on the beam, either to the left or right of the section, is known as the shear force at a section. Here you can see the shear force diagram at x. Bending moment at section. The algebraic sum of the moments of all forces acting on the beam either to the left or right side of the section is known as bending moment at a section. Here you can see the diagram of bending moment at x. So we have to discuss about sign conventions for shear force, either it is positive or negative. So here you can see the positive shear force and negative shear force given in the diagrams. And sign convention for bending moment. The bending moment is considered as sagging bending moment if it tends to bend the beam to curvature having convexity at the bottom as shown in the figure given below. Sagging bending moment is considered as positive bending moment. And hogging, here I am not discussing about hogging, but it is negative, it is positive, and the hogging is negative. Variation of shear force and bending moment. Variation of shear force and bending moments for various standard loads are as shown in the following table. Variation of shear force and bending moments. Type of load, SFD and BMD, means shear force diagram and bending moment diagram. Between point load or for no load region, the shear force diagram is horizontal line and bending moment diagram is inclined line. For uniformly distributed load, the shear force diagram is about inclined line and the bending moment diagram is about 2-degree curvature curve, means parabola. And for the load uniformly varying load, the shear force diagram tends to 2-degree curvature parabola and bending moment diagram tends to 3-degree curve, means cubic parabola. Sections for shear force and bending moment calculations. So how we calculate the shear force and bending moment? Here we can see shear force and bending moments are to be calculated at various sections of the beam to draw shear force and bending moment diagrams. These sections are generally considered on the beam where the magnitude of shear force and bending moments are changing abruptly. Therefore, these sections for the calculation of shear forces include sections on either side of the point load, uniformly distributed load, and uniformly varying load, where the magnitude of shear force changes abruptly. The sections for the calculations of bending moment include position of point loads, either side of uniformly distributed load UDL and uniformly varying load UVL and couple. Note, while calculating the shear force and bending moment, only the portion of the UDL, means uniformly distributing load, which is on the left hand side of the section should be converted into point load. But while calculating the reaction, we convert entire UDL to point load. Let us consider that cantilever beam AB is loaded with uniformly distributed load of W per unit length over the entire cantilever beam as displayed in following figure. So in next slide I have printed the figure. There we can see the measurements. Let us consider one section XX at a distance x from free end, that is from end B. Now we will have two portions of the beam AB, that is left portion and right portion. Let us deal with the right portion here. You can also go with the left portion of the beam in order to draw shear force and bending moment diagram. Let us assume that Fx is shear force and Mx is bending moment at a section xx. Shear force at section xx will be equal to the resultant force acting to the right portion of the section. Therefore, shear force at section xx will be written as mentioned here. Fx equal W into x. As we can see here from above equation that shear force at section xx will follow the linear equation, and on the basis of value of x we can conclude value of shear force at critical points, that is at point A and at point B. Shear force at free end, that is at point B, x equal 0. Therefore, f of B equal to 0. Similarly, shear force at a fixed end, that is at point A, x equal to L. So, Fa equal to W into L. X is replaced with L and Fa is equal to W, where W equal to W into L. Fa equal to capital W. Here you can notice the difference between small w and capital W. Now we have data for shear force at critical points, that is at a point A and at a point B, and as we have stated about the shear force at section x's will follow the linear equation, and hence we can draw the shear force diagram. Shear force diagram as displayed in the following figure. So this is the shear force diagram of cantilever beam carrying uniformly distributed load. Here the load is W. It is calculated in Newton per meter. The distance is x. So we can see the figure of cantilever beam. Bending moment at section xx will be written as mx. It is minus of totally uniform load into the distance between section xx and mid of and point of action of total uniformly distributed. This negative sign indicates the shear force diagram, as we discussed to the previous slides, the sign conventions of shear force diagram and bending moment diagrams. Mx equal to minus W into x by 2 because it is uniformly distributed load. So Mx equal to minus x minus W into x square by 2. Above equation indicates that bending moment at section xx will follow here the parabolic equation. We will conclude here that bending moment at xx will be negative. We can also conclude that here that bending moment will be directionally proportional with the square of the distance x. We can secure here the value of bending moment at critical points, that is at point A and point B. Bending moment at free end, that is at B, value of distance x is 0, therefore MB equal to 0. Bending moment at fixed end, that is A, value of distance x equal to L, so MB equal to minus WL square by 2 and MB equal to minus L by 2, where W equal to capital W equal to small w into L. Thank you.